welcome to Unapologetically Technical. My name is Jesse Anderson, and this is the show that's different. We go deep, we go all the way down. With me today is Donnie Greenberg. He is the CEO at Runhouse. Welcome to the show, Donnie. Would you mind introducing yourself a little bit more?
Yeah, thanks for having me, Jesse. As you mentioned, I'm the co-founder and CEO of Runhouse. Been working on Runhouse for a few years now. I'm based in New York, and we primarily focus on solving the problems of the interfaces to AI infrastructure, um, opinionation, the kind of history of AI infrastructure, and the pains involved in day-to-day work, research, production, et cetera. That's kind of our broader scope, and that's what I've been working on for quite a while now.
Oh, excellent. Well, I'm excited to talk more about AI infrastructure. It's all the rage now, and I would have never guessed it. I don't know, maybe you would have, but I would have never guessed we'd be talking about it in the industry, but lay people are talking about it. Actual news articles are talking about it.
Yeah, I mean, it's certainly not easy to explain what Runhouse does to my friends and family still. But yeah, I think the presence of this sort of like baseline GPU kind of discussion certainly makes it a little bit easier to ground the importance and the multi-billion-dollar investments of nation states, et cetera.
It's multi-billion dollar. Yeah, at one point I saw that Sam Altman was pitching a $1 trillion investment in data center, and that we'll see if that happens.
Yeah, there needs to be some new metric for like GPU spend relative to margin.
Or venture capital.
Yeah, right, exactly.
But you're looking at your education, your background is computer science, math, and finance. Do you think that you can do all three of those at once with good coverage?
Um, I think it's a little bit of a commentary on the kind of like American undergrad, American undergrad system. You know, like there's a, I think you can get generally good coverage, but just completing coursework is rarely enough to like get a real understanding of a particular area. I think that's like the most that's like particularly glaring in like finance and computer science. So I think the question is like, can you do enough outside to actually understand the sort of goings on or the state of the art in finance or the state of the art in computer science? And that's a lot more challenging, but I think I spent a pretty serious amount of time trying to get kind of like a real world experience in all of these areas. In finance, unfortunately, I think that the only really way to do it is to actually work in it. And once you choose to work in it, you know, it's a little bit of a one way door for a lot of people. So that was the one that I felt like studying it in school gave me the least exposure to what it was really like on the ground. And once I saw what it was really like on the ground, it was not particularly appealing to me. But overall, it's still come in handy. Like it's nice as a founder to have a stronger understanding of the the incentives of various different players within the venture ecosystem and within the even like kind of enterprise spending, like the enterprise kind of world, especially in response to like interest rate changes and things like that. But would I say that I have a strong finance education? Probably an inexperienced one.
Well, you referred to it a little bit, getting furthering your education, where you did your internship at Citibank and Goldman Sachs. That was one thing you learned. Did you learn anything else that you brought to now?
um I think that my interest in the finance world was that my in undergrad, like everything was a lot more theoretical. The computer science and the math world is, a little bit, I would say, detached from the sort of like, it feels a little detached from like industry more broadly. And so my internships were like, it came from a desire to be more deeply embedded in the like goings on of the economy. And I think there was a little bit of like a rude awakening to be so exposed to the sort of internal workings of how like large M&A decisions are made, and even like I worked in finance for a short time after school and like didn't uh, I kind of was a little bit surprised at how much money moves on the basis of kind of like very emotional decisions. Like this person's not happy about the vibe that they got from the Sprint CTO on the earnings call, that kind of stuff. So I think like my exposure to like how significantly the psychology of the financial markets affects the macroeconomy was a little bit of like rude awakening, but also like very important to see, right? Like I think maybe it was a reflection, maybe it was a little bit of a precursor to my experience now as a founder, where inside of like big tech companies, you're very you're encouraged to just focus on product and engineering excellence, and the idea is if you just sort of solve those things extremely well and keep your view of the world very elegant in that way, that like everything is going to work out in the end. And then I think in this sort of, as a founder in the real world, things are just like much hairier and messier, and maybe seeing the financial world early on was like a good or it was a good kind of initial exposure to that.
It's interesting. I've heard this from others where they say we justify with logic what we thought of with emotion. Where yes, we had this emotional reaction, and then we justify it in some fashion of here is the logic that got me there. People say that with buying all the time. You wanted to buy that, and now you're looking for the justification to buy that.
Yeah, I think the flip side of that is like much more pernicious. Like when you're doing like enterprise selling, and it's this really opaque, somewhat emotional, somewhat procedural, somewhat technical process, and you're trying to solve it like a puzzle, and it's not a closed system. It can't be solved. If you're not realistic about that, it's a very frustrating experience.
Well, out of those frustrating experiences, you went to a new frustrating experience at Google as a product manager. Why did you go from more the software side into product management?
So I was actually hired at Google into a sort of strange role for the time, which was like this hybrid product engineering role specifically for like supporting extremely technical products. So the product I worked on was called Ad Exchange. It was basically one of the like core pipes that the digital ads on the internet flow through. It was essentially an auction system where when like a user loads a page and there are empty ad slots on that page, they fire off to an auction system like the one I worked on to actually get bids for ads in real time. And so all of our customers were extremely technical bidding organizations that needed to be able to consume hundreds of thousands of queries per second to be able to keep up with the auction and place bids effectively, place ads effectively on behalf of their own customers who are the advertisers. And so I kind of occupied this like hybrid role that I don't really think even necessarily exists anymore. It was a little bit of a strange place to operate, like between product and engineering in that way, because you didn't have enough time to really like take on engineering tasks like any other engineer. Like you couldn't take something out of the roadmap, but at the same time, like you needed to be really deeply aware of the like technical constraints and costs when you're doing things like prioritization, because you have to operate at like a lower level as a PM. I think it was overall a very positive experience for me because like it opened the door to just like technical product work in general for me. I think like product work has a few different lanes. There are your PMs who are like just hardcore execution, kind of they have a sort of like extremely on the ball air about them. You have your like extremely marketing kind of evangelist PMs. And I didn't really know a lot about the PM world that was just like extremely technical, like focused on developer experience, integration, technical excellence at the like basically focusing on the technical success of one's own customers. And ultimately, I think that's just the direction where I've gone in my career, like being competitive via technical excellence, especially at the interface points, like the developer experience and the opportunity, like giving an elegant world for your customer to play in, to have their own opportunities to succeed. That was the training that I got at Google, working on such like a technical product as a PM.
What do you think was, other than the technical challenge in that being in the interface, what was so interesting about the problem for you?
I think one, it's not very widely understood in the world. Like, I think most people believe that they have a rough idea of like how ads are bought and sold, but really, I mean, everybody has their theories about how their devices are spying on them, et cetera, et cetera. But really, like, the underlying mechanisms are relatively straightforward, and once you see them, they make sense. But they're not understood. And I love to just sort of get underneath a system like that and feel that I have like a very deep understanding of something that, something that is a that we're exposed to in our day-to-day lives. Um, so there was just like at a baseline level, the mechanisms were very interesting. The sort of sub economy of digital ads is very interesting. I also think that there was a part of it that kind of goes back to my points about finance. Like, there was a part of it which had to sort of balance the traditional advertising world, which came from handshake deals and lots of really personal relationships and like irrational behaviors in some ways, and this just like extremely hardcore optimization side of the advertising world, which is basically like some of the largest models on the planet consuming hundreds of thousands of data points per second, and thousands of people banging on those systems to eke out additional revenue, additional performance, over a decade or more. So like that, viewing that like machine, I think was very interesting. It's as a technically curious person, it's a really fun playground because, and also like within the sort of tech kind of reward hierarchy, it's great. There was kind of a joke at Google that like everybody's promotion packets were like change two lines in a proto buffer made $600 million, because like there really was just this machine and it was delivering results that you really couldn't get any other way. We could prioritize one ad over another on a per impression basis in a space of thousands of ads and or millions of ads, billions of impressions. Like, there's something that's really appealing about that machine. At the same time, it's so narrow, it's so it's so isolated within the economy that you're sitting there in this like subworld just thinking like, what else could I do with this? Like, where else is this even applicable? And there are not really a lot of places that it's applicable. And when you see that it is applicable, it's only kind of frustrating that like you could never actually make that happen. Like, when you look at the efficiency of the digital ad auction system, and then you look at the inefficiency of the like airline ticket pricing world or the generic drug pricing world, it leaves a lot to be. It's very inspiring and uninspiring at the same time. So I think that was like a cool education, because I don't really think there are that many corners of the world that are so hyper optimized, hyper efficient, and kind of like modernized forms of something that was extremely handshake and kind of opaque, maybe even 20 years ago.
Of all the things that you dealt with, saw, what's one that stands out as being, oh, that was incredibly surprising, or I would have never thought that it did that.
Um, I think I was very I was very positively surprised by Google's ability to maintain a very human centric and thoughtful approach about systems that were so metric centric and kind of optimizable in nature. And what I mean by that is like, one, there really was a consistent baseline discussion and like everything that we did about what this actually did for users and what this did for publishers, like a particular project, how it would affect the publishing ecosystem, how it would affect users, how it would affect the advertisers. And I think maybe obviously lots of people have all different kinds of experiences in big tech. But to me, I was honestly surprised by that because I think it's just something that's extremely challenging to do at scale. And even at the level of like performance reviews and promotions, there was always this like human discussion where half of how you were evaluated was maybe on the basis of like the metrics that you hit, but half of it was your inputs, like how sound your reasoning was, how effective and well conceived and well executed the actual work product that drove that outcome were. All those things, like it's not so much a matter of like technical excellence. It's actually just something that I can't believe that Google has achieved at the scale of like 50,000 or something employees. And I actually don't really feel that it's present across the corporate world. Like, I don't think that in most companies there is this like baseline value for kind of like the human thought, sort of human centricity and thoughtfulness about decision making. I think that was also very well characterized by in the ad world, anything having to do with stripping away information and data is like really, really terrifying to people because that is just how that is what feeds the machine, the context about where this impression was and what else that cookie has, visited before for this particular advertiser, et cetera. And there was just like a very healthy privacy discussion as just like a baseline throughout all of like everything that we did, even to the point that like deprecating third party cookies in Chrome and things that I think were required a very, very like long term view of the ecosystem were very readily discussed. So that was like very positive for me. And I also think like it's important to get those experiences early in one's career so that you know that it's possible. Like, I think it's really easy to go get into like finance or digital ads and basically just see it as like a pure optimization game with sort of no human centricity, no like room for human centricity.
Interesting. So from Google, you went to IBM, but you changed things up a bit. You went into the quantum computing applications researcher as a tech lead. Why'd you make such a big change into quantum?
Um, I I was always very interested in physics. I tried to keep up with physics as much as I could through undergrad and then through like my early years of work. I had an inclination towards research. I think especially working in digital ads, I could see where like, fundamental research delivered transformative results, but I didn't feel like I was getting to work directly on that kind of like pure exploration. And my objective at that time was basically to get a job in research without having to spend 6 years in a PhD, if that were even possible. And then it turned out that it was by, a few happy accidents. So, I mean, I spent close to a year looking for roles in genomics, neuroscience, other areas of physics, and then eventually quantum computing. And it took a very specific need in quantum computing for me to actually have an opportunity to go into like a pure research role without a PhD. And the need was basically the type of technical facilitation and product work that I did at Google, where you're working with like ad agencies and you're working with people who cannot be exposed to the full technical guts of what you're actually selling, but still need to be actually brought to success and brought to a place of understanding and brought to a place of confidence with the product. And that was actually what quantum computing really needed at that time. We had at IBM a bunch of large research partnerships with like huge banks, energy companies, universities, and government labs that were just getting started with quantum computing. Quantum computing is so extremely different as a computing paradigm from anything in the traditional computing world that you can't just do a couple hackathons, expose people to the APIs, teach them a little bit of linear algebra and like set them off on their own. You needed to like use a tremendous amount of brain power to figure out how to actually get these people ramped quickly without having to like feel comfortable with the gnarliest bits of quantum information and quantum physics. So the research aspect of it was what was initially appealing to me. That technical challenge and my background working on those types of challenges was the way that I actually was able to get that job. And then in practice, I think it ended up really being a lot of what I did. I did a ton of these kinds of education and joint research activities with people who had extremely valuable experience and expertise to bring to the quantum algorithms and quantum application space from other areas, but needed to be ramped on the computing paradigm as fast as possible. So, for example, a quantum chemist at an energy company or at a national lab, or a combinatorial optimization expert whose PhD was in ship routing, you know, or someone whose background is optimization within options pricing and portfolio optimization. These people have the keys as far as the actual applications of quantum computing that need to be unlocked, but getting them productive and getting them feeling like they can actually get something done in their own space with quantum software was the big challenge, and that was basically what I did for 2+ years at IBM.
Generally, you do that with libraries and compilers and optimization that way. Do you think we're going to get there with quantum, or is it just too difficult?
What's interesting is that, like, you can't drop in the computing paradigms that worked well for classical computing um, as interface solutions for quantum computing. What I mean by that is, like, the I often, when I was like, people would get really frustrated with the 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 messiness of quantum information. Like, quantum computing and quantum information is a very difficult paradigm to, like, wrap your head around. And I think actually, even in, like, the fundamental, like, in the quantum foundations is like the area of physics that kind of reckons with these, like, really fundamental questions of our understanding of what's actually happening in quantum systems. And, like, I don't think that most physicists feel comfortable with their understanding of what is quote unquote happening. And so when it's somebody's, like, job to come in the morning and use a quantum system to do something productive, it's like it can be a very frustrating experience at first. And the math is, I think it takes some getting used to. And topics like compilation and even like higher order languages, and um, uh, like even kind of like the way that people are accustomed to using centralized computing resources, like mainframe or cloud style computing, like those aren't exactly transferable. A lot of the time I would tell people, like, quantum computing is to classical computing, or sorry, classical computing is to quantum computing as like a knife is to a blender. Like, they're just so extremely different that it's like very difficult to take the things that you know about how to use a knife and then apply them to, like, how to be good at using a blender. That's like a very imperfect analogy, but it's just like it's good at taking you out of your mindset. So where we felt that the strongest areas for delivering abstractions were basically out at the algorithmic level. So, like, in quantum computing, you have low level hardware, you've got the actual qubits, you've got like um, uh, basically whatever interaction model. Usually, it's some sort of like laser impulse, or there's different like qubit. There's different like architectures, but you've got the low level qubits. You've got something which is actually allowing you to interact with those qubits while preserving the purity of their state and like the quantumness of the system. And that interaction model is way too complicated for users to understand. I mean, you're blasting the qubits with like microwaves in such a way that they have their state altered in a mathematical sense that basically is like impossible to explain from like a traditional computing paradigm. Like, they're not bits that are being flipped. And so you need to take that and you need to expose it to the end user in a way that is not purely linear algebra, because if you abstract it too far and you make it so that they're thinking of this as some sort of like pure matrix multiplication, you're actually leaving a lot of optimization on the table. Like, there's a lot of really interesting things that you can do when you are aware of the specific operations in a high level sense that are happening on the qubits, and at least what can be toggled. So like a good example of this is that if you do quantum machine learning, quote unquote, where you try to optimize a system through gradient descent by envisioning that the quantum system is like matrix multiplication, it performs horribly because you have to do way too much hoop jumping to translate the user's high level parameters into what's actually happening on the device. But if you let them actually directly optimize, like you make the waveforms themselves that are the operations on the qubits parameterizable, then you actually get much better performance. So we needed to like basically give people the right abstractions where they knew, okay, this is sort of an algorithmic primitive. Here are the parameters you can toggle. Here is the physical motivation for it as far as what's actually happening on the device. And then here's a library that shows you a dozen different examples from these papers of this algorithmic primitive actually at work. And I think that like this is a little bit of a moving target. I mean, I haven't worked in quantum computing in a few years, and the devices are much larger now and they're much more performant. And so maybe more of a linear algebra kind of abstraction is okay at this point. But at that time, I mean, you were trying to give people something that they could just run and see what the toggles were and optimize it and then adapt it to something that looks like a ship routing problem or to molecular dynamics simulation. Compilers is like I think a little bit away. Like we don't really have high level languages yet, to be honest. We're still just like kind of mucking about in like bits directly.
That's interesting. In fact, it pairs with what I read about early languages when people were moving off machine level coding to the higher level languages. They were saying that the people who did the machine level coding usually didn't like the high level languages. So you basically had to start fresh. And I'm wondering if it will be a similar thing, is that we'll have this generation of people who I guess would be quantum native, or to put it a certain way, and that they carry forward. And that'll be interesting. So
I think
from IB, I'm sorry, go ahead.
my colleagues have adapted so fast to the changes in the devices and the changes in the algorithms. I think that's just like the nature of the field. Like what happened over the course of maybe like decades in classical computing feels extremely compressed in quantum computing. And all of my colleagues, like whenever I'm catching up with what's going on in the quantum algorithm space, it's like it's dizzying. It's just like I don't even think I would really be able to like be productive for at least a few months in the space before, like with the amount of like adaptation I would need to do to my understanding of the computing primitives, even.
Interesting. So from IBM, you went to Meta, where you were the product management lead, and you started being the product manager for PyTorch. At that point, PyTorch was already around, but you were starting to lead it. Is that correct?
I started off, there was already a product lead when I joined, who his name is Joe. He's amazing. He incubated and grew the PyTorch ecosystem for many years before I joined. He is actually back there now and is the product lead again for PyTorch. I started off focused on more of the like the direct, kind of similar to what I was doing in quantum computing, more of the direct relationships and product work that needed to be done between PyTorch and the specific subfields of machine learning. So PyTorch initially did very well in computer vision. And that was also to some degree because deep learning initially only did well in computer vision. So when PyTorch first came out, it actually came out alongside Torch Vision, which was the computer vision kind of bolt-on library for PyTorch with lots of state-of-the-art models, or rather like near state-of-the-art kind of industry standard models, transformations, primitives, and even like full end-to-end kind of training script reproductions of famous papers, just so that when people were picking it up and using it, they could feel like they didn't have to completely reinvent the wheel and recreate their entire ecosystem around compute or their entire kind of like personal workspace in PyTorch just to be able to try it out. That didn't happen as cleanly in other areas like NLP, speech, robotics, recommendations and ranking. And these other areas were becoming extremely well established. Like in 2015, 2016, computer vision was probably like the focus for the vast majority of deep learning researchers. But by 2018, it was becoming quite a glaring gap in the PyTorch ecosystem not to have strong NLP tooling. I joined in 2020, and the NLP ecosystem at that time, this was around the time of, or a little after BERT had like really taken off, and the day to day.
NLP being natural language processing.
Yeah.
The precursor to a lot what we're doing now.
Yes, exactly. Like the domain of text in general, you could call it. I mean, text is a little bit of a simplification because you shouldn't include like all anything that's represented that can be represented in text and that, but language in particular was like really taking off as like an effective deep learning domain, compared to, let's say, like more traditional methods. The text ecosystem at that time, the NLP ecosystem at that time, was also getting this massive community surge around Hugging Face. Hugging Face was basically just delivering incredible out of the box tooling, models, data sets, Python primitives for people to work with, and really saved us, I feel, in the PyTorch ecosystem, when we just didn't have the text tooling to keep up with the progress in the field. And then speech also was exploding. Like around the time that I joined, there was a really famous paper called Wave to Beck that some people treated as a sort of BERT-like moment in speech, where all of a sudden we could do things with deep learning on more of an end-to-end basis across many different tasks that previously we would have had to do with like extremely heuristic, human-tuned kinds of methods. And then recommendations and ranking also did not have really much of a set of community primitives, didn't really have much direct say about, in a library like PyTorch. And so, and it was like arguably the most successful deep learning domain, maybe still today in history, but at that time, certainly it was the most successful deep learning domain, just with the Google and Facebook, ad systems, feed ranking systems, et cetera. So I started off just focused on all of these domains. And then over time, I took on a broader and broader scope, the like core primitives of PyTorch, compilation, distributed, quantization, etc. And then eventually took over as a product lead, and it was like an extremely chaotic experience supporting 300 or so engineers working on very bottoms up kind of community driven deep learning framework. I wrote like 25 to 30 planning docs every 6 months for a period of time. But it was like a lot of fun, and it was very different from IBM because the community was so much larger. Like the community in quantum computing, the number of people who could use the libraries that I worked on, it was open source and it was great, and it was like very hard DevX and abstraction challenges. But in PyTorch, and at IBM, the people who are using those libraries would be like maybe in the dozens, right? There just aren't that many quantum computing researchers, whereas like decisions that we make in PyTorch affect hundreds of thousands of developers using PyTorch on a regular basis, and many of the teams building the bleeding edge models and systems that my friends and family are actually consuming on a day-to-day basis. So that was very fun.
One of the things you did that you didn't get into the specifics of is you said that you helped modularize some of Facebook's monoliths. What were the monoliths, and why did they need to be modularized?
Yeah, because of the pace of deep learning, and especially in the recommendations and ranking space, a lot of the decisions and the opinionation that were built into Facebook's internal systems that seemed safe and defensible at the time actually like aged out within a couple years. And like I think this is actually a very consistent theme within machine learning infrastructure and systems. You have like ranking system which is trained over millions or billions of users, trillions of posts and entities. So it's operating at like truly massive scale, like one of the largest machine learning systems on the planet. You have to make trade-offs. You have to introduce opinionation to be able to achieve performance, and you try to do it carefully that you're not going to like close doors in the future. But like for a long time, the largest models at Facebook and Google were linear regression. Like even deep into the deep learning world, like into deep learning being successful in many domains, even in the recommendation and ranking domain, the largest models were still massive regression models. So you can imagine that when all of a sudden something, a scale tips, and now actually for that scale, deep learning is more effective, which has happened a few times that like the scales have tipped in that way. Now you've just got to completely tear it down, right? Like there's just no way that you can take a regression training system and use it for training and serving a deep learning model. They're just too fundamentally different. The computing paradigms are completely different. So at that time, when I was being pulled into a couple of these re-architectures, one of them was with our data systems. We had very maybe I would say sort of Spark-like kind of compiled DAG data systems where you had to be able to express the processing that you were doing as a graph of operations that were going to get lowered onto some distributed pool of compute. And we realized that a lot of the operations that we were doing actually would be much more performant if they were running on the CPUs attached to the training machines or even on the GPUs themselves, like certain transformations, et cetera, make more sense on GPU. And so having the fluidity to move the data pre-processing around and not just take it as this graph that gets lowered onto a large pool of CPUs turned out to save like an absurd amount of compute and money. And we had to just re-architect a lot of things to be able to accommodate that. That was one system. We actually ended up open sourcing a lot of parts of that system as a project called Torch Arrow and another called Torch Data. Um, and then another big re-architecture was to the recommendations and ranking modeling. We hit a point where Instagram Reels and Facebook Reels and Instagram Stories, several of these systems that are really, really sensitive to recommendations and ranking, the models were just not nearly big enough. They just needed to be like 10x the size to actually be competitive. And these are already some of the largest models on the planet. And so we just had to completely tear down the recommendations modeling stack. We completely need to tear down the set of abstractions that a ranking or recommendations researcher at Meta would use to construct their model or their algorithm, rebuild it from the ground up. And then we actually also open source that as a system called TorchRec. And that was a very fun and interesting time open sourcing Meta's like ranking and recommendation systems. And then finally, I was leaving, or rather, right shortly before I left, I was basically being tasked with fixing this sort of the state of training frameworks inside of Meta. So training evolved in many silos, especially kind of domain specific silos. Like there was a training framework for text, there was a or there were multiple training frameworks for text, multiple for image, multiple for video, multiple for ranking recommendation, etc. And there was just a huge amount of overlap, and none of them were particularly good. Like none of them were particularly pleasant to use and unopinionated and future proof to the next few years of innovation in these domains. And so we were basically asked, like, what does a generic access to training, compute, and training abstractions look like that we can multiply the productivity of a typical researcher or a typical engineer and eliminate this really long research to production, production to research time that we were experiencing. Um, and when I looked at that problem and I could see that it was very present across the ecosystem, people complain about, Airflow hell, notebook hell, translating into various different form factors, Docker images, SageMaker, Kubernetes, et cetera, just in the normal course of like building any sort of machine learning system. We had our own analogs to that problem. I could see that this is a problem kind of more broadly in the ecosystem in AI infrastructure, and decided like, all right, I can probably solve this in the sort of more general form externally in open source.
We'll get to that in a second.
Yeah.
So that you touched on this double digit savings, where if I understood it right, you were talking about more doing a data locality on a single machine rather than doing a lot of outreach. Is that Did I understand that correctly?
So the way to think about it is like pre-processing for large for training is mostly streamable operation. And I say it's mostly streamable because there are a lot of like running metrics that you might need to use, like window sizes, batch norms, things like that, that make it so it's like ever so slightly not streamable. There's a lot of stuff which is purely not streamable. It tends to be more upstream in the processing, like joins and those kinds of things that are completely not streamable. I mean, you can do kind of like streamable analogs to them, which I think is done to some degree. There's a lot of filtering, balancing values inside of the data sets that require kind of consistent metric tracking. But for the most part, you could think that like a lot of the gnarliest parts of the data processing happens earlier in the processing, and those are going to happen in like traditional Spark-like massive processing systems. And then as you get closer and closer to the model, you actually are operating on your batches that are just about to actually be passed in. And so then a lot of that processing is actually purely streamable. So and a lot of that processing might even be like, tensor level kind of processing, like flips and rotations and augmentations in the case of images, or normalizations, things like that, that might actually be more performant on the GPU. In some cases, like in video, GPUs actually have on hardware primitives like discrete cosine transforms that are designed for processing the data much faster than on CPU. But I will say, like that should be taken with some grains of salt, because we even found that some there are scale questions, there are performance questions for every one of these data primitives. All of them behave differently. So it's not such an obvious thing like, oh, let's just try to put as much stuff on the GPU as possible. What you want is like a lot of flexibility in how you choose to move things on local CPU processing, distributed CPU processing, and GPU. And so what we basically found was that if the last bits of that like streamable activity could be moved onto the CPUs of the machine that is holding that the GPUs are attached to, that you saved probably like 3 or 4 separate nodes of your distributed processing to just put it onto that. Like, the compute power is equivalent, right? But just in terms of the communication overhead, synchronization, things like that, you save like 3 or 4 nodes of processing just by moving it onto those CPUs. And then the flexibility to move some things on GPU too is very nice. And a really simple example of why moving things onto GPU can be nice is that the certain formats are highly compressed in the way that they're actually stored and loaded in the pre-processing stages. And then when they're decompressed, they get much larger. And so if you move the compressed data over the GPU bus, you end up saving a lot of time relative to decompressing it on CPU or decoding it on CPU and then moving it over the bus in much larger format. So, you want just an extreme degree of control over all of these over these decisions. And our starting point was no control. It was just everything happened in that Spark like distributed environment. So just by giving the engineers much more control over what happened where, ended up yielding like a nation state's worth of power savings in our training data centers.
That that's funny you talk about the power savings. Um, I think it was Meta's new data center. Did you read about that? And is it Louisiana or Mississippi or something?
It's
God, I
can't
think
keep
it's
track. Yeah.
yeah. It was going to use an entire large city's worth of power. So yeah, crazy. Well, let's talk about um, let's talk about your new company. And to do that, let's switch over to the whiteboard. Now that we're whiteboarding, let's talk about what is Runhouse.
Yeah. So the problem that I mentioned before, like at the interface to infrastructure, that I think that was a very long-standing problem, but it became exacerbated as models and systems got larger. So the way to think about the problem is basically that the vast majority of the world in the software world, up until that point, relied on kind of two mechanisms for scaling. One where there's more mechanisms, but let's just to be really, really simplistic for a second. One mechanism for scaling is basically like web service style scaling, where you're able to develop some kind of subsystem, like a microservice, whatever is your unit to be scaled. You always develop it elsewhere, right? It's fundamentally kind of a single box representation of your program, single server, single machine, whatever you want to call it, container. And then when you want to scale it, you can horizontally scale it, deploy it to a system like Kubernetes, and then you end up with like a number of parallel replicas that are able to serve your application at greater scale, basically. Um, so that basically you take one input and it gets farmed out to many replicas. But the point is that the application itself needs to be is developed as a single machine program, right? Even if you end up vertically scaling it to some degree, it's still ultimately something that most of the time you can actually run on a laptop. Then in the data world, you had more of a lowering style scaling, which means that you take your program, whether it's a SQL query or like a series of data frame operations, whatever it is, and then you trace it out into some kind of DAG, and then you basically take that representation, that DAG representation of the computation, and you lower it into a distributed system like Hadoop or Spark or whatever else. And then that basically takes all of those sub computations and it schedules them on all the available compute on the cluster, and it wires up the communication between them. And the interesting part of that is that you can optimize a lot of pieces of that compute graph, and you can often slice off small subsets of your data to represent the computation on like smaller scale. Like basically, you can take the same compute graph and often lower it onto a much smaller compute for development. And then when you want to do it at scale, it works pretty much exactly the same way. You just lower it onto much more compute. So the machine learning world largely adopted the first type of paradigm for inference, where your model is serving sort of like a web service. And so you can kind of get it working on a single machine and then scale it up horizontally, and largely adopted the second paradigm for training, where you need to submit some kind of workload onto a scheduler that can take your graph of operations and lower it into your available compute. And the AI world, I feel, really over optimized for the constraints of 2016 machine learning, where the thing that had gravity was largely the data, meaning you wanted to take the program and send it to wherever the data was. And they also were running practically only CPU. There was really very little GPU machine learning in big tech. The people who were producing machine learning frameworks at the time, it was practically all CPU. And so you can take a DAG like this and just break it up into essentially a series of containers, and then just sprinkle it onto the available compute in whatever data center your data lived in. And so you really wanted to be able to capture it as a fully idempotent, isolated algorithm. What that also meant was basically it was horrific to develop. When you think about the DAG itself, in this case, there's really no small scale local development. Like in the data world, you can't just, you can try to slice off a portion of the data, but for the most part, these are not runnable locally. And so we created these stopgaps for being able to do local development. And those were hosted Jupyter notebooks are a classic example. You SSH basically into the machine with your compute, and then you transform it. You basically transform your program into this sort of facsimile of the real algorithm, get it working, and then you need to translate it back into your kind of scalable DAG later, which can take months in many cases. And the DAG in this case is often something like Airflow or Kubeflow pipelines, or one of basically something that looks like that basically comes from the data world in a sense to be able to orchestrate these programs. Distributed is another constraint where you just don't have GPUs or multiple GPUs or large scale distributed compute attached to your laptop. So there's pretty much no way, even if you were just to look at a single element of this program and try to develop it directly, there's no way to actually develop it. So what this ended up producing is this really, really bad research to production, really bad developer experience for researchers and for production engine and for production machine learning engineers, the researchers had basically no proper dev experience where they could write their real code. They always had to write sort of facsimile, tiny sandbox code where they can't actually get their algorithm working on the real data or the real compute. And then they need to babysit this like long translation process into production where it can actually run on their real scaled compute. But then once it's already translated into this DAG format, it's just unusable. Like you can never develop it again. You can never make a one-line code change. You need to like translate it back into notebook land to be able to really like innovate or develop it. And what that meant in practice is that nobody wants to touch these things ever again. So what we envisioned as a solution to this problem broadly, both on the inference side, where nowadays their models are larger, they don't always fit on a single machine. You've got multiple models as really the expectation rather than the exception for machine learning systems today. Meaning your machine learning system is often calling into multiple models in sequence, or has some actual
orchestrator pattern.
Exactly. And so, the problem exists there too. You just can't develop these systems locally. So the solution that we've built is called KubeTorch. And it basically, one is a recognition that the machine learning ecosystem has completely converged on Kubernetes, that with very few exceptions. Even the people who were kind of served well by systems like Slurm before, now with RL, much more heterogeneous workloads, much more demanding fault tolerance needs, are now basically moving to Kubernetes just because it supports the heterogeneity of the workloads the heterogeneity of their workloads. But so one, it's a recognition that the world has moved to Kubernetes. Two, it's a recognition that the machine learning world needs to use Kubernetes differently than the rest of the world, which is that we can't assume that you can develop your code elsewhere and then containerize and deploy it. You have to actually be able to use it like a mainframe, like a shared compute pool for your development and for production. And so what you want to be able to do is use Kubernetes almost like a process pool inside your program. So you can say, oh, within this part of my program, I want, 10 GPUs. Within this part of my program, I want 32 CPUs and I want them to be running Spark. And with this part of my program, I want to so you want to actually, the subroutines of your program, you just want to be able to tap into your pool of compute on the fly and then have really fast development and iteration with that compute natively in local Python. And when you're ready to run it in production, it runs identically to how it ran locally because it's just Python and it runs inside of Argo or Airflow or whatever or GitHub Actions or Fast API, whatever you use to actually schedule and run your application in production. So that's the kind of high level of why we need this in machine learning. It solves this like research production problem, but also like it's a very different world from the it's a very different paradigm from the other forms of scaling we already have.
Makes sense. Okay. And so Runhouse does this for you automatically. Runhouse does what for you?
Yeah. So we do a couple things. One is that we built KubeTorch. So KubeTorch is basically this like eager mode. Eager mode is a term that kind of like when you compare like PyTorch and Kubernetes, PyTorch and TensorFlow. TensorFlow makes you write your computations as a graph. PyTorch lets you just write regular Python and it will execute the operations that you tell it to execute on the GPU kind of fluently and natively with a lot of debuggability and control. So that's why we call the system KubeTorch. It's not PyTorch specific, but we basically have built this eager mode Python interface into Kubernetes where you can launch and wield your Kubernetes resources for writing and iterating, debugging, deploying machine learning workloads, scaling, etc. So that's all open source actually as of last week. And then we also basically offer a few other like helpful a few helpful products that basically kind of complement it. So for one, we have like a serverless product that is currently in alpha. So if you don't have experience with Kubernetes, if you want the industry standard and you want the scalability, the stability of Kubernetes, but you don't want all the complexity of understanding all the nuts and bolts of what, all the configuration, the integrations with the cloud providers, the, massive ecosystem of observability and scheduling, et cetera, et cetera. So we can actually just manage the Kubernetes cluster for you in our cloud account or in yours. So it's kind of we're unopinionated from a pricing and from a tooling perspective, whether it lives in our cloud account or yours. And we call this kind of like serverless without regrets. It's basically you get the joy of not having to manage the servers, but you don't have to worry that we're charging you some kind of highly opaque markup or that you're taking like a big latency speed bump for the for the data to leave your own cloud into ours, or for it to leave your security boundary. And then if you want the cluster to actually be inside of your own cloud account, we'll manage it in your cloud account as well. That's it's basically exactly the same product. It's kind of like on-prem or like in VPC serverless. And then we also just basically package a number of observability and prioritization, bin packing, optimization, management tooling with KubeTorch for more like kind of enterprise users. But the core of the solution, the thing that I set out to solve at Meta, this problem of the interface into the compute, that is solved by just like the core open source KubeTorch, and it works for any type of machine learning workload with any type of scaling. So it works for training, inference. It works really well for RL. Like we've seen actually a lot of teams basically moving to KubeTorch-like primitives and kind of hack together KubeTorch-like compute models for RL specifically. Code sandboxes for agentic workloads, single controller frameworks like Ray, or PyTorch just came out with their own called Monarch. So you can kind of give your researchers and your machine learning engineers KubeTorch, and it can sort of to them be like a serverless platform for running any and all their machine learning workloads at any scale. And that's kind of the core thing that we produce as the solution to that problem.
So KubeTorch in this case would be much more. You didn't say it was analogous to PyTorch, but it's that same sort of programming interface for people.
Exactly. So the reason that we call it KubeTorch is basically that in PyTorch, you have a GPU or whenever you have a device, an accelerator attached to your machine that you're running PyTorch on, and you call my model or my tensor dot2, this is like this dot2 API that actually sends it over the GPU bus over onto the accelerator. And then once it's over there, really PyTorch is actually operating over RPC to control and manipulate the objects that are in GPU memory there and do GPU computation. So you get this like extremely fluent, debuggable, extremely fault tolerant interface into your to be able to wield your GPUs. And we give you the same thing basically for your compute in Kubernetes. We use this .2 API. You can take any function or class and also data and basically dispatch it over onto essentially arbitrary compute on the cluster. It could be distributed, it could be auto scaling, it could be single controller, et cetera, et cetera. And then you just use that object that we give you back, which is identical to your original function or class locally in Python, but you're actually wielding like large scale compute with it on the other side.
Makes sense. So if you go to whiteboard 2, you'll see the diagram that I made. So make sure that the diagram that I'm making for you is correct. So I didn't put arrows in, but we've got objects, as you were mentioning. So we'd have KubeTorch running here on a particular machine using those RPC calls to these other machines where it's actually bringing those objects back. Is that correct?
Yeah. So like I would say the model is sort of like this. Like you have, let's say, your actual Kubernetes cluster is represented by this circle, and then you're creating containers inside of the cluster when you request resources. Your actual machine is out here. Like your actual machine is basically outside of the cluster while you're actually doing development, and KubeTorch is basically making it so that local Python can actually command around resources that are on the cluster. So it's almost like it's sort of flipping the compute model from Airflow, where you take your program and you lower it into their system, and you take your job and you send it to compute. In KubeTorch, we take compute and we bring it back to you, and then you can fluently use it however you like, run arbitrary things on it, debug it, um, browse around the file system, PDB debugging. It feels like local development. And then within this actual container that's on Kubernetes, you've got your GPUs, you've got CPUs, you've got whatever accelerated compute that you want. One of the nice things about this is that like you don't even need to be able to run the program locally at all to be able to actually like edit and debug it and iterate it just in a local IDE. What I mean by that is like you might have Mac OS in your dev environment, but you might be running VLLM in your inference pipeline, multiple models, whatever inference pipeline, and you can just natively use VLM inside of your program because it's really running inside of the remote compute. It's actually VLM isn't even installable on Mac OS. So, the fact that you can do that kind of heterogeneous development is really good for like pipelining models where they all have different dependencies, or ML pipelines where this thing needs to run on Spark, and then this thing needs to run with Ray, and this thing needs to run with PyTorch distributed, and this thing shouldn't have any of them. It's a code sandbox, and it should be really bare. And then when you're
It's a
done,
much better paradigm for the notebooks, where instead of you being constrained to that notebook environment, now you have a different way of doing
exactly. And I think that notebooks are great, and notebooks are really good for like education, exploratory data analysis, like collaboration, but they're not, they're the things about that interface that it can be preserved while also being able to wield, like break out of the notebook's compute sandbox and wield large scale compute. So you can use notebooks as KubeTorch just in Python in the notebook. You just pull in the compute that you want. The nice thing, though, about everything being in Python is that the moment that you're ready to run this in production, this little, I don't know if you can see my pointer here. This little,
it. No, use the little laser, bottom left one.
okay. So this little, um, uh, laptop here, which is actually running the Python program as I'm developing it. When I'm ready to run it in production, first of all, I can run it in my like CI environment, like GitHub Actions. Okay, so this is not even the laptop; it's just a totally different environment for automation. Or I can run it whatever I do my automation, and then I can actually move the program into the cluster, and it's going to run in production inside of Argo or Airflow or whatever inside the cluster, and it's utilizing the exact same compute resources identically. So it's like it's running 100% reproducibly, not sort of like hopeful reproducibly like notebooks to Airflow, like 100% reproducibly. And if something is breaking in production, you can just grab that code and start running and iterating it and debugging it from your laptop because you're running on identical compute when you're running it locally from your laptop.
And how would you know that you're running on identical data as well?
So identical data is a harder problem, or is another hard problem. What you'd really want is basically that, like, I believe that a lot of reproducibility that people want out of the data layer actually comes from really good version control. Meaning, if you can capture your programs completely in version control, then you have like really, really good time travel to the exact version of your data, assuming that you're using like a sufficiently flexible data foundation. So, for example, if you have like a good lake house, like if you're using like Iceberg or something like that, and you have the ability to specify data versions, then in your code, when you're running your daily processing, your daily training, whatever, it's going to be identifying the data version that it's working on in code. And that gives it a sort of reproducibility that if you then pull down that code and start working with it locally, it's pulling the exact same data because it's running inside of your cloud and it's pulling directly from S3. Like all those connections are there. You don't have any of this sort of craziness of like engineers loading specific data into this like Wild West environment of their notebook or their laptop or whatever. It's all end-to-end systems that are being built that should run identically in production.
Okay. And although you have this more on the training side, do you handle inference too, or is that something separate?
Yeah, so it works basically exactly the same way. So the Python program that I'm showing you here, it looks like training because it's got 3 replicas. This is SPMD training, like single process, multiple device, or multiple data. Basically, just like when you take your program and you just duplicated n times in separate processes on separate nodes. This is just like, a classic training primitive that you need for all different types of machine learning activities and training, or in like, embarrassingly parallel data processing. But the, slight difference of how that compute is used is no problem for us because Kubernetes supports all of this. So that's like probably, the most important the most important aspect of Kubernetes for our purposes, the fact that it is truly, truly unopinionated. And it's the only thing that it can provably run the full scope of machine learning workloads that any organization today, and probably for at least several more years, can need to run. And what I mean by that is, like, if you're in Slurm, Slurm is really good for launching like a training workload, or like embarrassingly parallel. It's really good at just launching n replicas of a program, but it has no concept of inference. There's no such thing as like a service in Slurm that can auto scale or even just like be separate from your compute. It requires a really, really homogeneous compute window. And similarly, systems like SageMaker training and SageMaker inference and SageMaker hyperparameter optimization, they're all really opinionated about that one particular workload, and they all have different abstractions, and they all have to be configured and optimized and observed slightly differently. And ultimately, most teams have actually moved to Kubernetes because if you're going to build a compute foundation with end-to-end prioritization and queuing and resource sharing and unified observability and unified auth and unified like dev experience for your own users, you want it to be able to support everything. And so that's what Kubernetes has emerged as. And for us to basically be able to launch an inference workload, the diagram actually doesn't look all that different. If you're building like a fast API app locally here, that fast API app might say, okay, I need a Llama model running on a GPU for this part of the app. Let's say it's a RAG app. You've got for the retrieval portion, you've got an embedding model that's running on such and such compute with such and such dependencies. Maybe it's running with Triton, and then NVIDIA's Triton inference server. And then you've got your the actual vector store portion of it, which maybe you run on separate compute, or maybe you just run it from inside of the Fast API app itself. And then lastly, you've got your generation portion where you need like an LLM. So your traditional token generation model, like Llama or Coin or something like that. So normally, if you're building this app, you need to actually deploy these as separate services to even be able to run and test your app at all. With KubeTorch, you just use that compute natively inside of your Fast API app locally, and the embedding parts go to the embedding compute that you allocate, and the Llama parts, the generation parts, go to the generation compute that you allocate. And these are just separate pods, and they can even be separate services, so they have auto scaling. And then when you're ready to deploy your Fast API app, it follows exactly the same path. It goes inside the cluster, and now it's serving, and it can be auto scaling. And all the replicas of your Fast API app can be calling into sharing the same embedding service and the same LLM token generation service. So all this auto scales really, really cleanly. So Kubernetes is like a flexible substrate for this kind of Fluent Python program is extremely powerful. It basically captures practically anything that you'd want to do as a typical machine learning researcher or engineer today in enterprise. There's one other thing I just want to mention about Kubernetes that I think is important to anchor. A lot of people have this association with Kubernetes that is kind of from the web world and is really, really complex. I think in reality, Kubernetes is extremely simple. It basically is just, if you have a bunch of machines and you have a bunch of applications that you want to run on those machines, you don't want to have to take each of those applications and right size them to maximally consume exactly the resources that they get when they get put on one of the machines. You don't have to like manually manage that yourself. If you containerize your applications, you can sprinkle them on the available compute, and they could become a lot more fungible. We have the exact same need in machine learning. You just want to be able to take lots and lots of sub applications, this inference container, this training worker among my training workers, and just sprinkle them on the available compute and share them with a bunch of other people as a kind of shared pool of compute. Kubernetes does that perfectly. A lot of the other stuff that you might need to like learn your way around in Kubernetes is stuff that like not shouldn't be expected of a typical researcher the same way that it shouldn't be expected of a front end engineer or a person building back end apps. They should be able to use abstractions to not have to worry about all that configuration, and that's what we basically provide.
Okay. And that's part of that cloud offering that you're mentioning, as well as
Yeah.
once you've built on the KubeTorch. Okay.
Yeah, exactly. If you have an understanding of Kubernetes and you use KubeTorch, you're going to get this extreme development development experience, iteration benefit immediately. Like the time that it takes to redeploy your application to Kubernetes to be able to test a one-line code change is often like 20 to 40 minutes. If you iterate with KubeTorch, it's like 1 to 3 seconds. And then you also get lots of fault tolerance benefits and scaling benefits. But that's if you're already, you already know what you're doing. If you don't know what you're doing, or you're afraid of Kubernetes as a beginner, then our serverless offering takes care of all that. You really just looks like a kind of serverless Python interface. You don't have to understand anything about Kubernetes to use it.
Okay. And so on your website, you talked about that magic iteration, and that magic iteration is if somebody's eyes are glazed over from what we've been talking about. Think of it this way: your data scientist's ability to ideate and hear and try something, even a one-line change, as you mentioned, sometimes that can be hours, depending on how you have things set up, your infrastructure. But here, what Donnie's talking about is something that you could do in potentially minutes, potentially much shorter amounts of time, simply because you have much better. Or I think you actually put it very interestingly: is we're stuck in some of these mindsets of the 2010s. We haven't moved into 2025 of this is how we can spin up processes like you're doing with Kubernetes. Is that a good summation?
Yeah, exactly. Like I think the machine learning world is very accustomed to executing via deployment. Like that lowering I was mentioning, where you take your DAG, your machine learning pipeline, and you send it to the compute to run. That is a fundamentally slow activity. I mean, it requires a long time packaging and scheduling, and your resources that you've allocated when you run the training one time and then hit an exception that you're debugging and make a one line change, all those and resubmit. Between those that first execution, the second one, you're basically just tearing down all of that you spun up. So the first time you run your training, you build a Docker image, you deploy it to SageMaker or Kubernetes or wherever is running your training, and it's going to bring up a bunch of containers, and it's going to load your data and load your model into those containers and do some setup, and then it's going to start running your program, and then it's going to hit an exception, and the moment it hits that exception, it's just going to cascade fail, destroy all that setup for you to just make a one line change and do that again. By making it so that we allocate the compute and quote unquote bring them to your program, they're actually held in place. So when you make changes, we actually hot sync and redeploy to the existing resources. So our end to end iteration time is 100 to 1,000x faster than if you were to do this directly on Kubernetes, because we're holding the resources in place. And our fault tolerance is really good because when you hit an exception inside that remote environment, we really aggressively hold it in place. We freeze all those resources, propagate the exception back to you, and then in code, you get an exception, which effectively is asking you, what do you want to do now? Do you want to tear down that compute and bring up larger compute because you hit an out of memory error? Do you want to just proceed on with training because actually that was just a blip and you're fine? Maybe you got a CUDA out of memory error, and that indicates that your batch size was too large. So maybe actually you just want to shrink your batch size a little bit and then proceed on with training of those existing resources. In practice, we've seen the fault tolerance, or rather unrecoverable failures in production, drop by like 99%, just because you can catch exceptions and choose what you want to do about them. So it's like, that what you just described is really just a mindset change of how you utilize the compute. Is the compute coming to you, or are you sending your job to compute and doing this crazy amount of setup every time, which is extremely wasteful?
Yeah, that all makes sense. In fact, some of this you're bringing up some thoughts that I guess I just always took them for granted as you were talking about the when you're using Spark, let's say, and something dies, it brings that whole leave down, you have to bring it all back up again. Whether your cluster's dead or not, it doesn't matter. Your DAG is dead and will have to be redone. So yeah, that's an interesting thought of being able to change it like that. Okay. Yeah.
And we took inspiration actually from the Spark Connect or Databricks Connect interface. Like I think that actually that is a really good model that is really well substantiated on the ecosystem. In Python, you just say, I want this compute and I want to run, and then you get back essentially like a pointer to your data on that compute, and you run operations locally in Python on that compute at scale. And then, like we see a lot of teams running single functions on Databricks Connect just because it's the easiest way that they have to take a function in Python and offload it to larger scale compute. But you just don't need to do that. You don't need to use Databricks Connect to run arbitrary Python. It's really built for Spark. So we've just taken this and blown it out for like arbitrary compute.
Okay. Are there any other parts of this that you want to talk about?
I think the RL is a really interesting reinforcement learning is a really interesting use case for the system that we've seen. And I guess I would just encourage people to go explore RL if they haven't already, because it's as somebody who's been in the ecosystem for a while, RL is very powerful and it's gotten very easy if you have the right infrastructure. Like the algorithms have gotten a lot better, and there's some Hello World examples that I think will really surprise people, and they open up a lot of use cases inside of like what we would call agentic, whatever kind of a task, higher order valuable task kind of machine learning that really weren't possible before. And as long as you have the right infrastructure, they're pretty fun and easy.
And these Hello World, are they on your website or where are they at?
We have a few RL examples on our website, like the Hello World on our site for async GRPO, which is like a light adaptation of DeepSeek's the big news making DeepSeek algorithmic unlock was a GRPO algorithm, and we have our own Hello World example of it. A lot of systems like Unsloth or TRL are good examples of systems that have simple notebooks for people to try single machine, but I don't think you have such an easy time getting those into production with into, let's say, a practical use case inside of a company. If you look at our Hello World examples, they're running on Kubernetes in a way that you could run them in production, and that's kind of a little bit. You read them in a little bit more detail, but they're very scalable and very flexible as like a jumping off point for if you're just getting started with RL.
It sounds like a fun weekend project. That would be pretty cool.
Yeah. The example that DeepSeek published that everybody basically uses for their Hello World is solving elementary school math problems, and that's just kind of cool to watch. I mean, you're watching the model do something in a way that you couldn't really watch it do when you were fine tuning BERT for sentiment analysis, and you're just watching a loss curve go down.
So, what's exciting you about your roadmap coming up?
So one thing is basically some of the companies that we have currently banging on it are just operating at a very large scale. We're not keeping a fleet of thousands of GPUs. So just like scaling is great because that's the benefit of doing this all Kubernetes native is that it's known to be extremely scalable. So that's exciting. Just like more of that kind of scaling and hardening. And I'm hoping our high level objective is basically to unseat Slurm in the research world and unseat SageMaker in the enterprise world. So if we can demonstrate that this system is performant and scalable enough that a company doesn't need to use an outdated system like SageMaker, that's very exciting to me. Other parts of the roadmap that are exciting are like the data layer, Kubernetes, and I think distributed in general, where it's not like a data-centric distributed program, like a data frame in in Spark, let's say. Communicating data across workers is never really elegant, and it's hard for users to use lots of the really fancy things that have been built for like fast data communication over like RDMA that NVIDIA and others have built. So we built this like new data layer that's sort of like blob storage, but for just like inside the cluster, and it's zero copy and it's really fast. And like that solves a lot of problems and just like the normal course of building an ML pipeline where you end up just bouncing a lot of stuff off of blob storage and slow or wasteful. Um, and we can do things direct GPU to GPU or directly in memory to directly in memory. So that's fun. Um, and some other things I think on the roadmap that are exciting is just basically like the like fault tolerance stuff that we can do, um, especially for like dynamically rescaling workloads. Unlocks a lot of like kind of holy grails in the ML infra world. So like dynamically resizing a training job or a distributed processing job is really valuable because then you can basically always max out your cluster utilization because when one job finishes, another job which is running can just size up to eat that capacity. And then when inference spikes or a new job comes in, then you can just scale it down. And today, the vast majority of teams leave like a crazy amount of headroom, like 20% of their capacity is basically sitting idle just to leave that flexibility for like development or for new jobs to come in. And we can just max out 100% all the time. And that also like opens up things like spot training where you can have spot instances coming in and out of the job at a time. So those are things that are exciting to me, but I think that like, they'll take some substantiation. I think when I talk to people in the infra world about this, they're basically their eyebrows raised and basically say like, I'll believe it when I see it. So I think the substantiation is needed there.
Well, I'm looking forward to seeing it too. Yeah, I've seen a lot of work go into that, and usually it was more around the machine learning side of, of, of optimization, trying to be able to predict when something would be done, so that it could. But it sounds like you're going about it a different way.
Yeah, I mean, for us, it's all about just like control of the compute. Like I was mentioning about that project at Meta, where we just by giving people more control over the compute from their data processing, they just we didn't need to reveal the whole gnarly sort of world of compute to them. We just needed to give them a little bit more control, and then they could do lots of really amazing optimizations to the placement of their programs, the organization, the communication. For us, like a lot of these problems actually just come down to control. It's just not possible today when you launch a PyTorch training job on Kubernetes. If the world size changes, that thing's just going to fully break. Or if you hit a CUDA out of memory error, the thing's probably just going to break. And then the whole thing just disappears. And you better hope you have a checkpoint. You have that like a little bit more control that you can orchestrate it from the outside, like you can do some really amazing things. And I think that that's kind of the theme of what we deliver.
Oh, that's really interesting. The I think people having watched the interview up to this point would say you're a pretty smart guy, but it's also funny that you also have titles: chief housekeeper, chief contractor, chief gardener, interior designer, house painter, private chef. What does all this mean?
Yeah, I mean, it was just kind of like a silly thing that we started when we founded the company. Like we needed titles. I don't really love like traditional software engineering titling. Like it's not super in machine learning in particular. Like the titles are kind of a mess. Like data scientist, machine learning researcher, software engineer, research engineer, et cetera, et cetera. Now I think actually a lot of people just use MTS, which is nice, and we kind of use MTS for like if we ever need like official titles. But so I just made it. We just basically decided like people need titles. They'll just be like you have to pick something of like some form of housework that you're really bad at. So like I'm not a particularly neat person, so I'm the chief housekeeper. Um, my co-founder is really not handy, and I think he's the chief handyman or something like that, or I don't know, a contractor. But the funny thing is that LinkedIn constantly notifies me about housekeeper jobs in my area, and I cannot turn it off.
The recommendation system's gone awry. That
Yeah,
is,
I mean, I can't knock those engineers. I'm declaring that I'm a housekeeper. So
yes. Maybe you need to air quote it, and then the algorithm will know. Oh, air quotes. That's different. Yeah, but I've seen startups do some crazy stuff. Like I think Josh Wills, his was data janitor for quite a while. If you look at his, but
yeah,
no, I haven't seen chief housekeeper before.
that's a good data janitor is a very accurate one. We had a different thing. We're not at this scale yet, but I always felt like the leveling systems in like big tech are so funny that they just like they took all the sort of flowery language out of it and just made it like a number. Like it always felt kind of like a Pokemon level to me. And then the way that people talked about other people, it was always like uh you had to do this like translation. So what we were going to do instead of like traditional leveling, we would have everybody basically join and get like a ladder, like a title of what they are, like designer, engineer, whatever, sales, like account manager. And then when you get promoted, you get senior tacked in front of it, so you're senior engineer, senior designer. And then every time you get promoted after that, you just get an additional very. So, after a certain amount of seniority, you're just a very, very, very senior engineer.
Or it could be like great uncle or great grandson. You'd just be great, 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 great grandfather.
Yeah, yeah, yeah. That's good. Just like great, great, great engineer. Yeah.
That's how awesome I am. I'm three greats level.
And then people are just going to be like, oh, he's a 3G.
Yes. Yes, that's what we do. And we were talking about before the whole reason we want to be that 3G or that software engineer 2 or whatever. It's funny because we don't you don't get promoted for doing something that's simple, something that's straightforward. You get promoted by over engineering something that nobody knows, and then you get promoted.
Yeah, I think actually the grade system of leveling of just adding grades is kind of apt because it kind of represents how much that you need to do a big thing to add a grade. Like you can't just sort of coast along and then be an even greater, be to be titled as greater. I heard just on that topic, I heard this hilarious thing last week that there's I'm not going to say which company I heard this about, but they apparently there was kind of like an understanding that you wouldn't get promoted in a given cycle, even if you just like absolutely crushed it, unless you, as part of whatever you did that cycle, you launched a new microservice, which is like a hilarious thing to optimize for as a company. Like, what a mess that companies' backends must be with people creating like additional contrived microservices just to go along with their promo packets. So, hopefully, we don't end up in any of those sort of like ridiculous anti patterns, especially now with like vibe coding and being really trivial to do any of this kind.
Another thing I noticed about your resume is you get things into things really early. How do you identify? Do you have a process? How do you know you're on the right track? You know something's going to take off.
Um, I I don't think of myself as like early in a lot of these things relative to like I guess most of my colleagues in digital ads and quantum computing and in AI, they were people who took like real bets, like they did their PhDs in an area that had absolutely no funding at that time, or like lots of people speculated would not be hireable. um I think I'm not so early that I need to actually like think 7 or 8 years into something to be able to really like ramp and get into the community. Um, that and therefore like the skill set of like being able to deliver powerful technical abstractions and um and kind of elegant like zero cost abstractive kind of interfaces to people, like being able to ramp people to be able to wield compute and wield their tooling powerfully tends to be needed at just about the time that I have come into each of these fields. So I think that maybe it's just like kind of indexing my career on that has brought me to some fields at good timing relative to them sort of becoming mainstream, because almost by definition, if you're trying to upskill a whole bunch of people to be productive with quantum computing, it's probably because it's about to go mainstream, and there are a lot of companies that are interested in training up their workforces. Um, so I think probably just indexing on that. I tend to be very skeptical in general of all of these fields, like these fields and others. And I think like having somewhat of like an investing mindset, if that makes sense. Like I tend to think of like years of my career as like investments, and like the specific things, gaps in my skill set, things I want to learn that I'm going to get out of those years are what I largely index for. And kind of corollary to that is that I tend to see, a major factor in the return that I get on that investment is how much resources I'm being given to kind of work with to do the things that I want to do in that time. So, for example, Meta PyTorch was very appealing to me because I went from a very small engineering team working on IBM's open source quantum algorithm software to 300 or so engineers to work with, and a lot more resourcing behind the projects that I wanted to do. So I think of things kind of in that ROI mentality, and in general, I find my life is a little bit more pleasant when I'm working in areas that are over resourced rather than under resourced. So that's like a little bit of a cheesy answer to follow the money as far as like where people are investing, and it's also incredibly dangerous with like state of the AI ecosystem right now. But I found like resourcing in terms of people has been like a good indicator of kind of where there's going to be fun.
Okay. Uh, yeah, I could see that. I think that's an interesting way of thinking about the problem. Okay. Donnie, thank you for coming on the show. I really do appreciate it. Thank you for sharing so openly.
Yeah, thanks so much for having me. This was a lot of fun.